Hello everyone, I'm Dr. Shruti Pandey from University of Louisville. We want to take a very basic question on three-phase power system or three-phase supply system. So before going into that question, let's have a quick brief review on the different kind of voltages, that is phase voltage, line voltage, phase current and line current. So before going into that, the thing which is there on the screen is a star connected system, a star connected generator which has three windings which are connected in form of star, which is this, right? So these are the three phases A, B and C. So there are basically two kinds of voltages. One is line voltage, which we also call it as live voltage, right? Or we call it as line to line voltage, right? So what is that? The voltage between two lines. So this is a line, this is a line and this is a line. So the voltage between two lines, that is VAB, this is VBC, and the voltage between line A and line C is VCA. So VAB, VBC and VCA, these are these line voltages. Okay, so why am I saying that these are equal? Because this is a balanced system, right? This is a balanced system. And what do I mean by balanced system? Like if this is a neutral, not if, it is a neutral. Like in a three-phase star connected system, there is always a neutral, which is this. There are three phases. One phase is this, which is phase A. One phase is this, which is phase B, right? And one phase is this, which is phase C. So I told you that there are two different kind of voltages. One is this line voltage, the other one is phase voltage. We'll talk about this balance system later. So one is this phase voltage. So what is phase voltage? The voltage between any phase and neutral. So that is this, the phase voltage of this will be VAN. The phase voltage of this will be the voltage of phase with respect to neutral, that is VBN, and similarly VCN, right? So there are two kind of voltages. The first one is line voltage, or we call it as line to line voltages, the voltage between two lines, and the other one is phase voltage between a phase or a line and neutral, right? So these two are the voltages. Now we are going to see that what is the relation between these two voltage. So you can see here, we'll take one line and one phase. So this is VA and this is VB and this is VAB, okay, and this voltage is VA. So what is the relation between VAB and VAN? And this voltage, if this is neutral, we can say it as that phase voltage of this phase is VAN. Okay, so you can yourself see that line voltage, which is VAB, it involves two phases, one this, one this, right? So definitely the line voltage must be greater than a single phase voltage. Okay, so the relation is that VAB is more than, and how many times more or how much more? It is under root 3 times more than this voltage. Okay, so this is a general relation that V line, which can be anything, VAB, VBC or VCA, any line voltage, is equal to under root 3 times V phase voltage. This is showing phase, right? So what are these phase voltages? VAN or VBN or VCN, right? So this is a general relation between line voltage and phase voltage in case of star connected system, right? We also call it as star connected system, star or Y. You can see, right, that this is in a form of Y. The structure or the winding is in form of Y. So therefore we call it as star or Y connection system. Now we'll come on the current part, right? So now you see that this is a line current, right? Line current IA, and the same current, it is traveling from here, and the same current, and this was phase, I told you, right, that this is VAN, or you can also call it as the current which is flowing in this phase or from phase to neutral. This is neutral point. This current will be VAN, right? The current between a phase and neutral. So you can see that the line current IA, which is coming across this line, is equal to this phase current also. So therefore the general relation is that line current is equal to phase current. So yeah, so this is these are the basic two formulas which you need to remember while solving any question. Then in case of star connected or Y connected system, line voltage is equal to root 3 times phase voltage, and line current is equal to phase current. The other thing is that this neutral, when I said that this is a balanced system, so by balanced system I mean that at the neutral point, the current which is coming from here, IAN plus IBN plus ICN, will be equal to 0, right? That there is no current here, or the sum of the current whichever is coming from any of the phase branch is equal to 0. This is what balanced system is. If this will be an unbalanced system, then this term, then it may be, there is a possibility that this AN value is greater than this ICN value, and this is IBN. So it may be a possibility that this IAN is greater than this BN and CN value if there is a case of unbalanced system. But right now we are only focusing on balanced system. So just a single thing to remember is that the sum of current at this neutral point will be equal to 0. So whatever current is coming from here, no extra neutral thing is required to feed back the current. Okay. So this was all about star connection. Now we'll come to delta connection. Similarly, what we'll see the voltage and current relation, or the phase voltage and line voltage current and voltage relation, or you can say the line and phase relations of current and voltage both. Okay, so in case of delta, what we see that again, this is a line current, these are three lines, right? So this line current, if the direction is given outward, if you consider the direction inward, you can consider it anyway, right? If I am right now taking the current inward, so I say that this is IA current. When this current is going to reach this point, it will get divided into these two parts, right? So if this is phase A and this is phase B and this is phase C, so you can see this clearly that this line current is not same as individual phase current, because this current, some of the current is passing in phase A and some of the current is passing in phase B. So this IAN or line current is not equal to phase current. So therefore the relation is this, that line current is greater, and how many, you can see that this line current is dividing into two parts, right? So definitely this line current is greater. We are applying KCL here. KCL is that sum of all incoming current is equal to sum of all outgoing current. So if this is line current is IA, that is equal to IAN plus IBN, right? And these two are the phase currents, right? So this is line current. So line current is definitely greater, right? And how much greater it is? That line current is equal to under root 3 times the phase current. The same relation which was there in star connection, the relation which is there between line voltage and phase voltage, the same relation is there between line current and phase current in case of delta, right? And now we'll see the voltage relation. So voltage relation is that we see that this is the voltage, this is A and this is B. So we see that this is the line voltage between two lines, which we are representing as VL. So this voltage is equal to the phase voltage. So phase voltage for B phase, this is the phase voltage, right? This is the phase voltage for A phase, and this is the phase voltage for C phase. One more very important thing which is to be noted here is that there is no neutral in delta, right? So there is no neutral in delta. So you can see that whatever is the line voltage, the same is the phase voltage. So line voltage is equal to phase voltage in case of delta connection. So just remember one of this before solving the question. Just remember just remember any of this. Maybe this one you can remember for the star connection, that for the star connection the line current is equal to phase current. That's the only thing you need to remember, that line current is equal to phase current in case of star connection or Y connection. Line voltage will be under root 3 times V phase, and exact opposite is in the case of delta connection. Okay, So this was all about generator. So these are the generator connection. So a generator is there. Inside that generator there are three windings. A three-phase generator is there, or three-phase source is there, because generator works or behaves as source. So a three-phase source is there, which is generator. It has three windings in it. So those windings has these kind of voltage and current relation among them. Okay, so now we'll move towards the load. So this is three-phase load. So in case of three-phase loads, like this is source side, right, and this is load side. So earlier what we studied was this kind of three-phase source, that one source is this, one source is this, one source is this. They all were connected in either star connection form or delta connection form. So this kind of sources were there. Now we are studying the load parts. So either in star form or in delta form, some loads are there, right? So this is star load and this is delta load. So the relation between the voltage and current, or you can say line voltage and line current, is exactly the same in case of loads also, right? So in three-phase load also, when we are talking about the star connection, line current is equal to phase current, which was the same in star connected source, and line voltage is equal to under root 3 times phase voltage, which was again the same in three phase star connected source. And similarly in case of delta, line voltage is equal to phase voltage, line current is equal to under root 3 times phase current. So the relation of current and voltage is same. Just you need to make this thing clear that this is a three-phase load and that was three-phase source connected in respective windings, be it star or be it delta. Okay, so these two things are important. You need to remember this. Yeah, now one more very small and important point is that the power consumed in one phase, right? We got to know that there are three phases. Okay, so the power consumed in one phase of the load. So this was three-phase load. These I am showing it with the help of resistor, but this can be any impedance, right? And by impedance I mean that it has a resistance also and it has certain reactance also. And by reactance I mean inductive reactance, that means an inductor is there, or capacitive reactance, that is a capacitor is there, right? So we are saying the power consumed in one phase of the load can be found if the current, resistance of phase are known. So if I want to find out the power across this phase, right? Let us say that this is A phase. So if I want to know the power across this phase, if I know the value of the current across this phase, that means I A phase, right? Or the phase current of that particular phase, which is A phase, and resistance. So if we are talking in terms of impedance, it will be I square ZA phase. And if we are talking only in terms of resistance, if there is no inductor or capacitor, only a resistor is there, then it will be I A phase square into R A phase, right? So this will be the value of, you can see I have given a general term, right? Any phase, be it A, B, C. I told you before in the class that phases can be represented as RYB form, ABC form, any form, right? The point to be remembered is that this is a single phase power, right? And this is I square into R or I square into Z. Now the total power consumed by the load, because the load is three phase, it has three phases. If we have taken the power value of single phase, we can do 3 times that power so that we can get to know the power of complete system. Okay, so if this is for single phase, power for single phase, the total power consumed by the load will be 3 times that single phase power. So that way we'll get power from all over the thing, all over the load or all three phases. Now the total power consumed in the load, what's the equation for that, right? If here the power was when only current and resistance, or current or impedance, that is Z, of a single phase is given, then we can calculate the power in this way. But if a normal voltage and current is given, how are we going to calculate the power? We'll see here. So it is that total power consumed in the load is PT, T represents total, is equal to under root 3 VL IL cos theta. Okay, so I'll tell you how this is derived. So you know that before this we studied that the power was EI cos theta, right? Where E was RMS value of V, I was RMS value of current, and cos theta was power factor, complete cos theta, and this theta was power factor angle, right? Power factor angle. And what is power factor angle? The difference between, or the phase angle, this theta is the angle between current and the voltage. And when what is the case when there is a phase difference, or this theta or this phi value exists? There are only two cases: either inductor is involved or capacitor is involved. Either in these two cases, this theta term will come into picture, theta or phi. Sometimes I just take it as same, sometimes I'll call it as theta or phi, right? So just consider it as same, do not get confused in that. So yeah, so if there is only resistive load, this cos theta value will be 1, right? Because in case of resistive load, there is no angle, or there is no difference between current and voltage. If voltage is like this, current is like this, right? So there is no phase angle, or there is no angle difference between this voltage and current. So theta will be 0 and cos 0 is 1. Therefore, in case of resistive load, this cos theta value will be 1. But there will exist certain value of cos theta when we are talking about inductors and capacitors. Okay, so we'll come back here again that yeah, so this was EI cos theta. Now if we are taking a 3-phase power in terms of phase voltages, right? So it will be P 3-phase will be 3 V phase voltage, because this was for single phase, right? So now we are taking for 3-phase. So 3 will be there, V phase, I phase, cos theta, right? So this was the phase value. Now if we want to, now let's take two different cases. One is star connected or Y connected, right? And one is delta connected, right? Delta connected. So we know that in case of star connected, we'll see at the upper side, line current is equal to phase current. Okay, so line current is equal to phase current, and line voltage is equal to under root 3 times phase voltage. Here it's the opposite. Line current is equal to under root 3 times I phase current. Line voltage is equal to phase voltage. Okay, so now we have this power term in terms of phase, and now if I want to convert it into line, so it will be P power line, right? So all 3-phase power line in all 3 phases will be, so I'm going to take this, so it will be 3. In place of V phase, I want to convert it in terms of line. So if phase is given, I want to convert it in terms of line, so it will be, I'll take it out here. So V phase will be equal to VL by under root 3. So it will be VL by under root 3. I phase is equal to IL cos theta. So this will be cancelled. So what is the value of power here? The line power is equal to under root 3 times VL IL cos theta, right? So this is the total 3-phase line power. If you want, you can derive this term. If not, then just you can remember this term, because you will see that in delta connection also we are going to get the same value of power, right? So only remember this power, that way you will be able to manage all kind of questions. So we'll see how we are solving it here. So again, this formula we'll take and we'll put the value of line voltages here, that P line voltage in case of 3-phase system, it will be 3. V phase is equal to VL, so I'll keep it VL. I phase, I'll take the value of I phase from here, IL by under root 3. So it will be IL by under root 3 cos theta. So this is cancelled. It will be under root 3 VL IL cos theta will be the value of power, right? So this was star connected system. So now you can see that if you want to know the power in terms of phase values, right, in terms of phase voltage, in terms of phase current, the power will be this. But generally you will deal with the power in terms of line power you are going to deal with. Okay, so remember this formula. So if you want to know the power across the three phase load in terms of line voltage and line current, not phase, line voltage and line current, it will be root 3 times VL IL cos theta. In case of delta connection also, it will be root 3 times VL IL cos theta. Okay, where these values are in terms of RMS, right? They are not peak values, they are RMS values. So that's it. Just remember these for 1, 2 and 3. Just remember these three formula for star and delta connection, and you'll not have to remember much because power is same in both of the terms, and voltage and current relations are exactly the opposite in terms of star and delta. So just remember one, other you will be easily you will be able to remember that. Okay, so now we are going to take the numerical in the next video.